Hello everyone, myself Atul Pandey and this is my capstone NSEM PPT. So this is my problem statement, machine learning and deep learning based hostage crime scene detection. Uh, that is, we have to develop a multimodal machine learning approach for hostage crime scene detection. In our approach, we integrate group emotion recognition, post recognition, weapon detection, and sentiment analysis to provide real-time analysis of the scene. So in this, my part is of group emotion detection. So difficulties in group emotion detection. So group emotion detection generally faces two difficulties. One is expression synchronization. That is, when group members try to synchronize their expressions, uh, what happens is that individual emotions get masked and complicates the emotion recognition. Second is scalability. That is, we have to develop such algorithms that can handle varying group sizes and dynamics while maintaining the accuracy. So the data sets used in this are for emotion dataset, we have used GAF 3.0, which is an image dataset RGB. It has three classes: neutral, positive, negative. These are some of the examples from the GF dataset. Second is VGF dataset. It is a video dataset which also has three classes: neutral, positive, and negative. It is multimodal. That is, it has both audio and video. Third one is the hostage dataset. It is our novel dataset that has around 909 clips taken from movies and series. All of the scenes are indoor scenes of both hostage and non-hostage. These include scenes with and without weapons, adding diversity. There are only two classes, hostage and non-hostage. It is also multimodal, having both audio and video. And these are some of the snapshots from the dataset. Next is approach. So for the frames, I have read several papers and have came up with some of the approaches. So in my approach, I have adopted a bottom-up strategy emphasizing feature level fusion. That is, I have taken facial features of individual person and then I have concatenated them or basically done some operations over them to make them into global representation. So in this, I explored several techniques like LSTM, weighted mean, and standard deviation calculations. Then after obtaining these global features, I have passed them to a classifier to classify the image into three categories: positive, negative, and neutral. So before going further, let's see what model we are using for extracting features for individual face. So we are using efficient net, which is pre-trained on VGG phase 2 plus robust optimizer. This is our proposed model, which I created in my last innovation lab. So this model performed way better than all the other models on FER 2013 dataset and FXNet dataset. So I chose this model as for extracting features from individual faces. So these are the approaches. So in my weighted average approach, I took the weighted average of facial features and I assigned weights according to their location and size in the image, basically according to their importance in the image. In my second approach of LSTM, I fed the facial features into the LSTM so that the layers can learn a connection between the faces. And the third, mean and standard deviation, I just took the mean and the standard deviation of the facial features, I concatenate them into a final feature. In all of the three approaches of weighted average, LSTM, and mean and standard deviation, we are tackling the problem of varying number of individuals per image. That is, we are solving this problem. So these are my experiments on GF dataset. So also what I have done is I have before even processing the images for facial features extraction, I have aligned the images. That is, I have aligned the images in such a way, I have aligned the image of faces of individual in such a way so that their both eyes come at the same level. This has improved the accuracy a lot. So as we can see, mean and standard deviation performed way better than any of my other approach. So I adopted mean and standard deviation with classifier as SVM RFD as my model. So these are the confusion matrices of mean and standard deviation. So as you can see, aligned performs way better than non-aligned. Then coming to the video. So now we have the overall feature of each frame. So what we can do is that we can now amalgamate these frame features into a single global video feature. So in this also I explored many things like passing frame features to LSTM or taking mean and standard deviation of features to amalgamate these frame features into global features. But the question arises, why to amalgamate these results of each frame? Why can't we have like individual results of each frame? So firstly, videos convey continuous emotional changes. So like if we have a result of each frame, so it will be confusing and tough for us to determine the overall emotion of the video. So hence we are amalgamating these frame features into a single global feature so that we can get a single emotion of entire video. So these are my experiments on VGF. So in VGF, there are some videos that are empty. That is, it doesn't has any faces in any of the frames. So in my first experiment, I have excluded those uh, I've excluded those videos, and in my overall experiment, I have included those videos. So as you can see, after aligning the faces, mean and standard deviation performs the best, having SVMRF as the classifier, giving me an accuracy of 65.59%. So these are the confusion matrices for my VGF mean and standard deviation. So this is my overall proposed model. What I'm doing, I'm taking a video, I'm extracting its frames, then I'm passing these frames to YOLO V8 for face detection. Then I'm aligning the faces. Then where I've got the faces, let's say I have got N faces and I have got T frames. So now I am extracting the facial features by EffectNet. Then I'm taking this. Then for each frame, I'm taking the mean and standard deviation of all the faces and concatenating them. So these are my final frame features for all the T frames. Then I'm taking the mean and standard deviation of all the frames and concatenating them into a single video feature. And then I'm passing it to the SVM or neural network or CNN and getting the output. So now let's compare our model with other baseline models. So these are the accuracies of different models on VGF validation set. As we can see, our model performs the best from other baseline models. So now let's test our model on the hostage dataset. So these are the results on hostage dataset completely based on video-based emotions. So in this, mean and standard deviation performs the best, giving me an accuracy of 88.42%, having SVMRF as the classifier, which is a very nice accuracy. This is the confusion matrix for the hostage mean and standard deviation, where 0 is hostage and 1 is non-hostage. So now coming on to the multimodal approach. Up till now, we have discussed group emotions based on video only. So in my multimodal approach, I have considered both video and audio as the two modalities. So what I'm doing here, I'm extracting the video features from the previously specified model and the audio features from the AST. So what I'm doing, I am taking these audio features and video features, and then I'm passing them to an attention block. And I'm doing this L times. Then the resulted audio and video features from the attention blocks are then concatenated and then passed to a classifier to give me the output emotion. So why I have chosen audio as my another modality? Since as I have analyzed, so audio is a key modality. We can judge from the high tone of a person whether the person is anger or in excitement, or from low tone we can judge that the person is sad. So how I'm extracting the audio feature? So I'm using audio spectrogram transformer AST. So what happens in this? Basically, audio is transformed into spectrogram images for each frame time, and then these uh, spectrogram images are passed to a transformer for image classification. So basically, we are converting audio into images, and then we are applying image-based classifications. So this is my attention block. As we can see, we have the visual modality and the audio modality. We are preparing the query key and value, and then we are doing cross attention. Then we are applying self attention, and then a feed forward, and then add normalize, and then we have got the final audio and video features, and we are repeating this L times. So what does self attention do? So self attention helps us to capture internal dependencies and highlight key features that contribute significantly to emotion recognition for that modality. While in cross attention tells us the correlation between audio and video features, and it tells us that which feature is more important in both of them. So this is my proposed model. I have my video frames, I have my audio, I've extracted features from the video as well as the audio and then passed it to the attention block. I've done this L times, then I've got the final video features, then I've concatenated these audio and video features, passed on to a classifier, and then got the output. So these are my experiments on VGF dataset. So I tried on different values of L. So as we can see, L is equals to 2 performed way better than any other, giving me an accuracy of 73.89%. This is the confusion matrix for VGF multimodal. L is equals to 2. And then I compared my model with other baseline models. So as we can see, my multimodal audio plus video performed way better than hybrid networks of audio and video and ensemble audio plus video models. And this is my proposed model for single modality. So my multimodal performed way better than any other models. Then I experimented it on hostage dataset. So for hostage dataset, again for L is equals to 2, I had the highest accuracy of 91.34%. So this is my confusion matrix. Thank you, everyone.